Right. Can you see my shared screen?
Oh, yes, we can see the screen.
All right, good. Right. So we are going to start with the question on hydraulics, right? Hydraulic systems. From the question paper that I sent you, it's question 3. Nah? Right. 3.1 states Pascal's law. So the definitions, I'm going to leave them for you to do on your own. Right. I am going to send you the the recording of this thing. Well, the recording, and um, I'm going to I'm going to convert this to a PDF and send it to you once we are done with the meeting. No? But
Okay.
as far as definitions go, unless maybe you need help with some definition, then maybe I can explain something. Aside from that, though, I won't be covering definitions on this session. Not really. Yeah. For instance, the reason for that is because most of these definitions, just like Pascal's law, have already been discussed in N4. Right? If you remember in N4 for hydraulics, in hydraulics and engineering science, N4, we cover what is this? We cover what is this thing? We cover hydraulic. Um, what is this thing called? So we have hydraulic pumps, we have hydraulic accumulators, and then hydraulic. Why am I forgetting this thing now? Mm, not hydraulic jacks. Let me just look at it quickly. Uh, hydraulic presses. Yes. All right. So that is what we cover in N4, and in hydraulic presses, that's how hydraulic presses operate. They operate under Pascal's law. Right. Any and all hydraulic systems operate under two principles. Right. They operate either under Pascal's law or Bernoulli's principle. Right. So if we have what is this? If we have a hydraulic system, it either operates under Bernoulli's principle or it operates under Pascal's law, right? And then the ones that operate under Pascal's law, right, are closed systems, right? So if you have a closed system, if you have a closed hydraulic system, right, it would operate under Pascal's law, right? And how you state Pascal's law is based on the system being closed. Are we together?
Yes, sir, we are together.
Right. For instance, how I would state Pascal's law is that Pascal's law states essentially that the pressure exerted on a fluid in a closed container, right? The closed container part is the critical part here, right? That for 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 Pascal's law to be applicable, right? You have to be looking at a closed hydraulic system, right? So the pressure exerted by a fluid in a closed container will be equal in all directions, right? Simply put, that is what Pascal's law it is, right? Okay, I said I wouldn't do this, but I've already done it, right? I've just given you Pascal's law in words, right? And then mathematically, this is how you express it, right? You say the pressure. So, for instance, if you're looking at, say, if you're looking at a what is this thing? A hydraulic jack, for instance, right? And a hydraulic jack has two pistons. One you can refer to as the plunger piston, the other one you can refer to as the ram piston. Right. So how you would express Pascal's law mathematically is you would say the pressure exerted by the plunger piston is equal to the pressure exerted by the ram piston. Right. And we know pressure is equal to force. So this will be force on the plunger divided by the area of the plunger is equal to force on the ram divided by area of the ram, right? So if you happen to forget how to express Pascal's law in words, right, just remember this: the pressure, or let's say the pressure in a system in a closed container, right, will be equal in all directions. Right? Simply put, that is what Pascal's law is, and this here can be a guideline. Nah. Hello. Can we continue?
Yes,
Yes,
we
you can
can.
continue.
All right. Now let's look at 3.2. 3.2, figure 2 below shows a mobile crane hydraulic cylinder with an internal diameter and length of 200 millimeters, that's the diameter, and 900 millimeters, that's the length, respectively. Inside the cylinder, there is oil with a bulk modulus of 1.95 gigapascals. The cylinder is subjected to a force of 5.2 kilonewtons applied on its piston rod during its operation. Take the modulus of elasticity of the cylinder material as 10 gigapascals. The adiabatic index is 1.4. Right. Firstly, let me just ask if you guys understand the term bulk modulus. If we talk about bulk modulus, do you guys understand what it is that we are referring to? He says yes, he says no, he says yes, he says no. Is it a yes or no?
I'm sorry, I don't understand.
Right. What about Young's modulus of elasticity? That's one you should know. When we refer to modulus of elasticity, that's Young's modulus of elasticity. Right. Now, Young's modulus of elasticity, right, is essentially the mechanical property of a material or a substance that resists deformation. Right. Simply put, that is what Young's modulus of elasticity is. Right. Now, bulk modulus is similar. Right. Not exactly the same. We can say it's more or less the same, but I think the term similar does this justice, or does this more justice. It's similar to what Young's modulus is, because Young's modulus and the bulk modulus, right, both fall under the the modulus of resilience of a material, right? You essentially get um, three modulus of resilience of a material or of a substance, right? That is Young's modulus of elasticity, the bulk modulus, right, as well as what is this? Shear, right? The modulus, the shear modulus, where you look at um, if if a material, right, is undergoing shear stress, right, that is when you look at the shear modulus, right? So bulk modulus, modulus of elasticity, shear modulus, all of that falls under modulus of resiliency, right? Now, bulk modulus, right? Bulk modulus is a mechanical property of a material that resists compressibility, right? Compressibility, right? So Young's modulus is a mechanical property of a material that resists deformation. Now, this one, bulk modulus, is a mechanical property of a substance or material that resists compressibility, right? Hence, how we even calculate the bulk modulus, or one of the ways in which we calculate bulk modulus, right, is based on how we calculate a material's compressibility, right? And how you calculate a material's compressibility is as follows. It's going to be 1 over K total. So this is just in general, is equal to the sum of the substances that are involved, right, in what you are looking at. So for instance, in this case, you have the substance, which is oil. So this would, for instance, be K oil plus 1 over the bulk modulus of the cylinder, right? This is the general formula of calculating compressibility, right? And then to calculate the bulk modulus, or the total bulk modulus, right, you then have to solve for the total. So solving for the total, so this would be Kt is equal to 1 over K, which is the bulk modulus of oil, plus 1 over the bulk modulus of the cylinder, or of the material of the cylinder, right? The inverse of that, obviously, right? And this is how you calculate the total bulk modulus, or the effective bulk modulus, right? But my point here is that how we calculate the bulk modulus is based on the materials, or yeah, on the material's compressibility. And how you calculate the compressibility of a material is, this is how you calculate it, right? So essentially 1 over Kt is equal to 1 over Pascal, right? So compressibility, how we express compressibility is per Pascal, right? It is essentially per Pascal, right? And then the bulk modulus, so K, will be in pascals. Are we still together? Hello?
Yes, we're still together.
All right. So that is what essentially the bulk modulus is, right? It is the mechanical property of a material that resists what? Compressibility, right? That is how things like submarines are able to survive below water, right? Because the material is such that it is made to have a bulk modulus that is more than the bulk modulus of seawater. Nah? Right, let's look at calculations. Right, perhaps let's first write down what we've been given. Okay, we can write down what we've been given here. All right, let's write down our given data. Right, so we have hydraulic cylinder with an internal diameter. So we have the diameter of the cylinder, right, which is 200. That's 0.2 meters per second. The length, okay, we can call this the stroke length, seeing that you're looking at a piston stroke length, which is 0.9 meters. All right. Inside the cylinder, there is oil with a bulk modulus. All right. So K of oil is 1.95 gigapascals. The cylinder is subjected to a force, right? A force of 5.2 Okay, we can leave this in kilonewtons. We can convert it in our calculations. Right. In fact, we can do that now. It's fine. So kilo is equal to 1,000. So this times 1,000. Right. So now this is in newtons. Right. During its operation, take the modulus of elasticity of the material as 10. So E of the material of the cylinder, right, is 10 gigapascals. And then the adiabatic index is equal to 1,4. The adiabatic index, we use this to calculate. So it sometimes happens that you have air trapped in the cylinder, right? And to calculate the bulk modulus of that trapped air, right, this is what you use, right? Use the adiabatic index, right? So that will be Ka would then be equal to the adiabatic index times the pressure, right? That is the pressure induced by the force, right, that the piston is being subjected to, right? And that is how you calculate the bulk modulus of the air trapped in the cylinder, if there is air trapped in the cylinder. Right, so this is all our given information. Any questions here? Hello.
I don't have any questions, so you can proceed.
All right. So let us look at 3.2.1. Right. Calculate the induced or the pressure induced by the force applied on the piston rod in kilometers, in kilopascals. Right. That's pretty much straightforward. Right. You've been given the force that the cylinder is being subjected to. Right. So to calculate the pressure, we know that pressure is synonymous with stress, and stress is equal to force over the area, right? So we have this force, and we have essentially the area, because we have the diameter, right, of the cylinder. Right, so that is why this is just 1 mark, because it's pretty straightforward. So 3.2.1. All right, you calculate the pressure. Just bear with me. All right, to calculate the pressure, pressure is equal to force over the area, right? And then we know, seeing that we're looking at a piston rod, the area will be of a circle. So pi over 4 times d, right? D squared. All right. So here we can manipulate this as force divided by the area, which is, right, the area is going to be pi over 4. But instead of writing pi over 4 here, you can have pi times d squared and then multiplied by 4 on the numerator. Right. However you choose to do this mathematically doesn't really matter. Right. I just prefer doing it like this. Right. So now you substitute. And in substituting, F is 5,2 times 10 to the 3 times 4 divided by pi times D, which is 0.2. So 0.2 squared. Right. And what do you get here? What is this equal to? Remember, your answer must be in kilopascals. They did specify here that the pressure induced by the force applied on the piston rod in kilopascals. Right. So what do we get here in kilopascals? Always
in
round off
kilopascals.
to 3 decimal places.
Oh, I got 165.521 kilonewtons. And kilopascals.
So 165,521 kilopascals. Right.
Kilopascals. Yes.
That's correct. Right. Now let's look at 3.2.2. Right. Calculate the effective bulk modulus of the system in gigapascals if there is no air trapped and K cylinder is equal to E over 2,5. Right. So they want us to calculate the effective bulk modulus, right, of the entire system, assuming that there is no air trapped in the cylinder, right? And given that the bulk modulus of the cylinder is equivalent to the Young's modulus of the material divided by 2,5, right? Right. Like I explained, how you calculate the bulk modulus or the total bulk modulus or effective bulk modulus is using how we calculate the compressibility of a material, right? Which is so this is going to be 1 over. So effective, we can use E for effective, is equal to 1 over the K of oil plus 1 over the K of the cylinder. All right. Now there's no, right, we are assuming that there's no trapped air in the cylinder, right? So these are all the bulk modulus to consider, right? And then to calculate the effective, so KE, we have to get the inverse of this. So this will then be equal to this here, right? The inverse of what we get here, right? So now you can substitute. In substituting, right, you have 1 over the K of oil. Right, the K of oil is 1,95 gigapascals. Right, remember that the effective modulus must be in gigapascals. So we can substitute, right, the values of our bulk modulus in gigapascals. Right, no need to convert to pascals. So K of oil is 1,95. Right, plus now the K of the cylinder. Right, you've been given here that the K of the cylinder is equivalent to E over 2,5. Right, remember that E is the Young's modulus of the material. Right, and the Young's modulus of the material is given as 10 gigabytes. Right, I mean gigapascals, sorry. Right, so this here is equal to E divided by 2,5. But remember here that you have 1 over the K of the cylinder. So essentially this is what you have. Right, and then to fix this from being an improper fraction, we can simply say multiply by 2,5 multiply by, what is this? By the 2,5. So essentially the 1 over K cylinder will then be equal to 2,5 divided by the E. Right, so we can replace this with that. Right, so essentially here you will have 2,5 divided by E, which is equal to 10 gigabytes. So this is 10. Right, now when you calculate all of this, what do you get in your calculators?
I got 1.311 gigapascals.
So 1,311 gigapascals. Right, just so we are clear here, let's say this is equal to for context, let's do this rather plus, and then right, 2,5 divided by E. Right, and then from here you then substitute, and then we get the 1,311 gigapascals. Right, any questions? No questions. Right, let's look at 3.2.3. Calculate the free play on the piston rod. Right, now they want us to calculate the free play on the piston rod. Right, they want us to calculate the free play. So it's 3.2.3. Right, now free play is the same as backlash. Maybe you can refer to it as backlash. Right, backlash is the same as the clearance. So free play, right, is the clearance between the cylinder's bottom dead center, right, and where the piston ends up. Right, so the piston essentially doesn't go all the way to the bottom dead center. Right, so that clearance that you get between the piston and the bottom dead center, that is what they're referring to here as the free play. Right, that's the clearance. Right, it's the clearance between the piston and the bottom dead center. Right, simply put, that is what it is. Right, so essentially free play is that clearance that I'm referring to. Right, it can be referred to as free play, also clearance, backlash. Right, any term that refers to essentially clearance or backlash can be used. Right, but for the most part, for this subject, they refer to that clearance as free play. Right, so whenever they refer to free play, just know they are referring to that clearance I've just explained. All right, and how you calculate that clearance is, now remember that Young's modulus of elasticity, right, it is equal to stress divided by what? Divided by strain. To remember this formula. Hello. Are we still here? Do you remember this formula of calculating Young's modulus of elasticity from engineering science N4?
Yes, Mr. Mteto, yes.
Yes. Right. Now, like I said, remember in the beginning, I made a relation between Young's modulus and the bulk modulus. Right. So that is to say that if this is how we calculate Young's modulus of elasticity, how we would then calculate the bulk modulus is you would then say the bulk modulus is equal to the bulk stress divided by the bulk strain. Right. Aside from how we look at these terms technically, right, from mathematically, right, or from a formula perspective, how these two are different is that the Young's modulus, right, we look at Young's modulus from a linear perspective. Right, for the most part, we look at Young's modulus from a linear perspective. Right, so we look at how the material is, or how the material deforms from a linear perspective, either from the y or the x-axis. Right, whereas the bulk modulus, right, we look at the deformation volumetrically. Right, that is to say that mathematically this would then be equal to, so bulk stress is synonymous with pressure. So this will be pressure. We know that stress is equal to F over A, right? The same F over A that we use in calculating this pressure, right? Hence me saying that we know bulk stress is synonymous with pressure. So instead of having bulk stress, you can simply have pressure, right? Divided by, now the bulk strain, right? Remember that's the linear strain when having to calculate, the strain when looking at when looking at the material from a linear perspective, right? We would then use the deformation divided by the original length, right? Whereas here, like I said, bulk modulus is more from a volumetric perspective. Hence, to calculate the bulk strain will be equal to, so the bulk strain is equal to the change in velocity, the change in volume divided by the original volume, right? So here you would have the change in volume divided by the original volume, right? This is the formula we use, right? And then, of course, you would then manipulate this formula so that it makes sense mathematically. By that, I mean you then have to multiply the denominator and numerator by the original velocity so that it makes sense mathematically. Hence, you will end up with pressure times the original volume divided by the change in volume, right? And from the change in volume, that is where you get your free play, right? Remember, we said the free play is the clearance, right, between the piston and the bottom dead center, right? That clearance is essentially a change from a linear perspective, right? Hence, to calculate the free play, we then use the change in volume, right? The change in volume, right, will be equal to that free play times the area, right? The area of the piston, right? And this here gives us the volume. Right? Remember, volume, or the units of measurement of volume, is cubic meters. Right. So do we know this is in square meters? This will be in meters. Right. The product of this gives us the change in volume. Are we together here? All right, so that is to say that to calculate your free play, it's essentially KE is equal to pressure times the original volume divided by the change in volume. Right, that's the formula we use. Right, and that formula, right, comes from this here. Any questions?
No questions, sir.
So everything's clear so far, ne?
Yes, so far so good.
All right.
Can we go back? Can we go back, Mr. Mteto? Can you go back to the free play because you have the change in volume time equals to. Is that the free play or is that F times
Oh,
force
free play.
times pressure?
It's free play.
It's free play.
Okay, let's.
I think it's gonna confuse us because we think it's force times pressure.
Yeah, I hear you. Times the area of the piston. Is it clear now?
Okay, just yeah, it's clear now. Thanks.
Right. Now at this point, we've already calculated our effective bulk modulus. We have pressure, right? And then we can get the original volume, right? So KE is equal to, so that's going to be the pressure times, and then the original volume. Original volume is equal to the area, so pi over 4 times the diameter squared times the stroke length. Right, so this gives us the original volume, right? This gives us the original volume of the piston. So divided by the change in volume, which, as we've said, is equal to the free play times the area. Right, and that area is equal to pi over 4 times d squared. Right, so essentially, mathematically, that cancels with that, and this cancels with this. Hence, you would then be left with Ke is equal to the pressure times the stroke length divided by the free play. Mathematically, this is how it works out. Right, and then from here, you can simply make free play the subject of the formula, as that is what we are looking for. Right, so making free play the subject of the formula, it means free play will be equal to pressure times stroke length divided by the effective bulk modulus. And from here, you can simply substitute, right, the pressure we calculated earlier and got the 165,521. Remember, that is in kilopascals. So we have to convert it to pascals. So we have 165,521 times 1,000, right, times the stroke length, which is that 0,9. So 0,9 divided by the effective bulk modulus, which we've just calculated and got 1,311 gigapascals. Right. Also, we now have to convert this gigapascals to pascals. So this is 1,311, and gigapascals is times 10 to the 9. Right. Now they said calculate the free play on the piston rod in millimeters, right? So whatever we get here, we must express in millimeters. So what are you getting here? So this is 165,521 times 10 to the 3 times 0,9 divided by 1,311 times 10 to the 9. Right? So I am getting 0,114 essentially millimeters. Are you guys getting the same thing?
Yes, Mr. Mteto.
Right. So this, so free play is essentially equal to 0,114 times 10 to the 3. Remember, this has to be in millimeters. So instead of writing times 10 to the 3, you just replace it with millimeters. Right. Any questions here?
All clear.
All clear. Okay. 3.2.4 calculates the bulk modulus of air, right, of air trapped in the system in kilopascals, right? Now we are assuming that there's air trapped in the system, right? And like I said, how you calculate that bulk modulus is by using this formula, right? You use the adiabatic index, multiply that with the pressure, right? So that is 3.2.4. Yes, 3.2.4. We are now looking for K air, and K air is that adiabatic index times pressure. Right? They did specify that it must be in kilopascals. Right? So we can use this exactly as it is. Adiabatic index is 1,4 times the pressure in kilopascals is 165. And what do you get here?
231,729.
231, comma
729.
729 kilopascals. Right? So 3.2.5. 2.2.5. Calculate the effective bulk modulus of the system in megapascals if there is a 3.2% volume of air trapped in the cylinder. Right. So now we are taking into consideration trapped air. Right. Hence, to calculate the effective bulk modulus, so Ke will now be equal to will now be equal to 1 over K of oil plus what is this, 2,5 divided by E for the K of the cylinder, and then plus. So there is 3,2% volume of air trapped, and how you include that in the formula is, you say the percentage of the air, volume of air divided by 100 times the K of air. And of course, all of that, you'd have to find the inverse of all of this. right, to calculate or to get the effective modulus. Right, then all you do is substitute here. So you have 1 over K of oil, which is 1,95 gigapascals. Okay, now they did specify here. They said the effective bulk modulus in megapascals. Right. So let us convert everything to pascals. So here you will have times 10 to the 9 plus 2,5 divided by the 10 gigapascals. So 10 times 10 to the 9 plus, and then the volume of air trapped is 3.2%. So here you are going to have 3.2% divided by the 100 times K of air, which we calculated and got the 231,729 times 10 to the 3. Right, and of course, we have to calculate the inverse of all this. Right, now punch this in your calculators and then give me the magnitude of the bulk module of the effective bulk modulus in megapascals.
Let's hope I'm correct. I find 466,474 mega. Then
Okay.
corrected.
I'm gonna calculate this one myself as well.
Yeah.
So it's 1 over
And
1,95
no,
plus
no. I
2,5,
think I see what my problem is.
10 times 10 to the 9 plus 3,2 over 100 times 231, what do I get the 799? It's 729. So I think I made a mistake here. It's 729, not 799. 729, yes. No, the gentleman that just gave us the magnitude. I made a mistake here. It's supposed to be 231,729,
Yeah.
not 79.
All right.
729 times 10 to the 3. All of this inverse. Right, so I am getting 7,202 megapascals. Just confirm if you're getting the same thing.
Yes, sir, I'm getting the same.
The same, no?
Yes, sir.
All right.
Yeah, it's correct. I think my mistake was there by the percentage because I already converted it. I've put it as it is. So
Okay. That's all right. So that is how you calculate this. And then 3.2.6 calculates the free play on the piston rod in millimeters if there is a 3.2% air volume trapped. Okay, so now they want us to calculate the clearance. If essentially our effective bulk modulus is the one we've just calculated. Right. Remember, at this point we've already established that mathematically the free play will be equal to this. Right. So here I was just showing you. Right. In this calculation, I was just showing you how we get to this step. Right. But now that we do know, you can simply use this as a formula. Right. Right. We can use this as a formula now. And then this is equal to the pressure is still the 165,521. Right. 165, was it 521 times 10 to the 3 times the stroke length, which is that 0.9, divided by the effective bulk modulus that we've just calculated, right, where we have 3.2% of the volume of air trapped in the system, right? So we use 7.202 times 10 to the 6, right? As things stand, whatever you get here will be in meters. That's the standard unit of measurement for free play, right? So here they did specify again to leave our answers in millimeters, right? So whatever you get here, you must convert it to millimeters. So what is our free play in millimeters?
20,684
20,684 millimeters.
millimeters.
Yeah. Right. So as far as hydraulic systems or simple hydraulic systems, this is probably the one part you weren't really familiar with, the bulk modulus, because we don't cover the bulk modulus in N4. We only cover Young's modulus of elasticity. Right. But now you know that Young's modulus of elasticity is actually part of the group of the modulus of resiliency. Right. And that's the bulk modulus is also part of that group. Right. So Young's modulus, you look at the deformation linearly or from a linear perspective. The bulk modulus is you essentially look at the same deformation but from a volumetric perspective. That's the major difference between the two. Any questions? Right. Okay, let's move on to what is this? The question on fluid in motion. I think that was question 6. Right. Remember, our assessment will have questions based on simple hydraulic systems, fluid in motion, and pipeline systems. Right. I will send you more questions to look at during the course of the week, right, before your assessment. So your assessment will be based on more or less those questions or the questions that I will have shared. Are we clear here? Hello.
We're clear, sir. Yes, Mr. Mteto.
Right. So question 6 is based on fluid in motion. Right. 6.1 briefly explain the following terms: laminar flow, turbulent flow. So that you can do on your own. What I can mention here is it doesn't really matter how you explain the two terms, laminar flow and turbulent flow. Right. You can explain the terms in terms of what laminar flow is and what turbulent flow is. You can also explain the terms using the Reynolds number, right? For instance, for laminar flow, right? So laminar flow, or for us to have laminar flow, right? The fact that the type of flow, right, essentially refers to the nature of the flow, right, and how we establish the nature of the flow mathematically is using the Reynolds number. Right? So to get laminar flow, the Reynolds number must be less than 2000. Right? Some textbooks will have 2500. Right? So you can say 2000, you can say 2500. I'm fine with either of those. Right? Depending on which textbook you are using. Because like I'm saying, other textbooks use 2500, others use 2000. Right? The point is though, you are able to explain what laminar flow is as a nature of flow using the Reynolds number, right? And for the nature of the flow to be considered as laminar, the Reynolds number must be less than this, right? And then for turbulent flow, the Reynolds number must be greater than 3000, right? Or for the nature of flow to be considered as turbulent, the Reynolds number must be greater than 3000. As the Reynolds number is dimensionless, doesn't have dimensions. So that is to say, if you choose to use the Reynolds number in your explanation, that is fine as well. As long as you show an understanding of what this nature of flow, laminar and turbulent, refers to. Are we clear?
We're clear.
Okay, let's look at 6.2. 6.2, oil with a relative density of 0.9 flows through a 50 millimeter diameter nozzle at the rate of 44.8 liters per minute. The coefficient of viscosity of the oil is 0.012. Right, so let's first write down our given data. Right, so we are given the relative density, right, of the oil. Call this. Now, this symbol is the symbol we use for density. Right, we can call the density, the relative density of oil. So R for relative, it is equal to 0.9. Right? And then we have the diameter. With the diameter of the nozzle, which is 0.05 meters. We have the flow rate. So we have Q. Q here is 44.8 liters per minute. Right? Now the standard units of measurement of a discharge or of flow rate is cubic meters per second. Right, so that is to say you have to convert, right? You have to convert this Q from liters per minute to liters per second. Right? Now you don't necessarily have to do this here. So here you can write it as liters per minute, and then you can convert it when having to do calculations. But it is important to note that the standard units of measurement for Q is cubic meters per second. Right? So if you are given any other units of measurement, you have to convert it to cubic meters per second. So this is 44.8 liters per second. Coefficient of viscosity of oil is this. The symbol we use for coefficient of viscosity is this here, referred to as mu. Right, mu for mu. Right. So this is equal to 0.012 Pascal second. Right. So mu, the standard units of measurement is Pascal second. Right, so this you can use exactly as it is. Right. 6.2.1. They say determine the velocity of water flowing in the pipe in meters per second. Right. That should be straightforward. Remember, Q is equal to the area of the pipe times the velocity of flow. Right. So it's a matter of having to make velocity the subject of this formula. Right. Before you do, remember that they've specified here that we should leave our velocity in its standard units of measurement, which is meters per second. So meaning that this has to be substituted as its standard units of measurement, which is square meters. This as well must be substituted in its standard unit of measurement, which is cubic meters per second. So let's first convert our Q. Right, so Q is in 44.8 liters per minute. So to convert from liters, right, to cubic meters, you have to divide by 1,000, right, or multiply by 10 to the negative 3. And then to convert from minutes to seconds, you have to multiply by 60. So this is going to be 60, right? And then our Q will be equal to, what is this equal to? 44.8 times 10 to the negative 3 divided by 60. Round up to 3 decimal places. Just 44.8 times 10 to the negative 3 divided by 60. Right. So here I'm getting 7.46 recurring times 10 to the negative 4. So the best thing to do here is to hit your engineering notation button. If you do that, you should get 746. So you should get 746, then round off to 3 decimal places, so 667. Right, times 10 to the negative 6. Now this is in cubic meters per second. Right, we take this approach, right, for accuracy purposes. Right, this is a very small number. Right, so to be more accurate, we must make sure that there's more numbers after the comma. Are we together there? Hello?
Yes, sir. We're following.
Right. So this is Q. This is our flow rate in cubic meters per second. Now we can calculate. Our velocity. Right. So we know Q is equal to A times V. Right. Therefore, meaning V is equal to Q divided by the area. Right. And then the area we know is pi over 4. So essentially this will then be Q times 4 divided by pi times d squared. And now you substitute. So Q is 746,667 times 10 to a negative 6 times 4 divided by pi times the diameter is 0.05. That's 0.05 squared. Right. So whatever you get here, because all the quantities are in its standard units of measurement. Right. So whatever you get will be in meters per second. So what do we get here? Are we still together here?
It's 0.380.
So 0.380 meters per second. That's correct. So that was 6.21. Pretty straightforward. 6.2.2. Now they want us to calculate the Reynolds number. Right. Now the formula for calculating the Reynolds number, right, will be the density of the substance that we are looking at times the velocity times the diameter divided by the viscosity, right, or the coefficient of viscosity. Right. So we must have the velocity, which we do, the diameter, which we do, and the coefficient of viscosity, which we do. What we don't have at the moment is the substance's the substance's density. Right. What we have instead is the relative density of the substance. When the substance is oil. Right. So using the relative density of the substance, we have to calculate the density of the substance. So bearing in mind That's where we need to calculate this, so we can calculate the density of the substance first. And how we do that is by using this formula. So if you have relative density is equal to the density of the substance, right? In this case, that substance is oil. But it's the density of the substance divided by the density of water, right? So that is the same as saying relative density is equal to. So because we know that the substance is oil, we can now specify and say the density of oil divided by the density of water, right? And then the density of water, we always assume is 1,000 kilograms per cubic meters, unless it has been specified differently. So if it hasn't been given, if it hasn't been given either in the problem statement or in the question, then you assume it is 1,000, right? Always assume it is 1,000 kilograms per cubic meters, right? So this is what we are looking for, the density of the substance of oil, right? So to get this, you make this the subject of the formula, right? Density of oil is equal to, and it's going to be this and that. So the relative density of the substance times the density of water. Right, the relative density is 0.9. The density of water is 1,000 kilograms per cubic meters. And what is this equal to? It's
900.
900 kilograms per cubic meters. Right. Once you have the density of the substance, then now you can calculate the Reynolds number, because you have the density of the substance. So this will be equal to the density of the substance is 900. The velocity is 0.380. The diameter, what is the diameter equal to? 0.05. Divided by the 0.012. Right, and this here will give you your Reynolds number. Right, remember, I did say that the Reynolds number is dimensionless. So it'll just be a number with no dimensions. So what do you get here?
The answer is 1,425.
1425. Right. Now, if you look here, the 1425, it's definitely less than 2,000, which means the flow is laminar. Right. Now, the flow of oil, or the nature of the flow of oil, will always be laminar because of the oil's viscosity. Right. Always. Right. Let's look at 6.2.3. The nature of flow of oil in the pipe. Right, so nature of flow, is it laminar, is it turbulent, is it transitional? Right, it's nature of flow. You look at your Reynolds number, right? You then say your Reynolds number. We can say here 1425 is our Reynolds number, and our Reynolds number is less than 2,000. Therefore, flow is laminar flow. And you get your 2 full marks. Any questions?
Questions, then.
Mm-hmm. Or no questions?
Yeah, no questions.
Oh, okay. I thought you were saying you have a question. All right. The nice thing about fluid mechanics is most of the formulas, most of the sections, right, are related. Most of the sections are related. If you look at measurement of flow, um, if you look at fluid in motion, flow measurement or using instruments, the measurement of flow, um, what is this? Pipeline systems, right? Flow through orifices, right? All of those sections or all of those topics are related, right? So if you are very good in one, it's likely you're going to be very good in the other, right? Most of the, like I said, hydraulic systems, right? They operate under essentially two principles, right? There are two fundamental principles for hydraulic systems, and those fundamental principles are that's Pascal's law and Bernoulli's principle. Right? Those are the two fundamental principles or concepts that hydraulic systems operate under. So as long as you understand that, fluid mechanics will become simpler or easier for you. Right, so we've looked at simple hydraulic systems. We've looked at fluid in motion. Let's look at a question on what is this? Pipeline systems. Right, let's look at this question on pipeline systems. Right, 8.1, state Bernoulli's theorem of energy. Right, so that you can do that on your own. Right, but Bernoulli's theorem or Bernoulli's principle is essentially it looks at the conservation of energies, right, in a moving fluid. Right, that is what essentially Bernoulli's theorem looks at. Right, it looks at the conservation of energy. Right, so all the energies involved, right, on a moving fluid. Right, so the standard energies involved, the standard energies that are involved, that will be your pressure energy, your kinetic energy, as well as potential energy. Right, those are the standard three energies that we look at under Bernoulli's theorem. Right, and then of course you find that there are losses in the system, right, which introduces other energies. But the three standard energies that Bernoulli's theorem looks at, or Bernoulli's principle looks at, are those three. Right, the pressure energy, kinetic energy, and potential energy. All right. Now let's look at 8.2. So let's look at 8.2. And it reads as follows. A 40 millimeter diameter pipeline is placed at a gradient of 1 in 100 over a length of 700 meters. The difference in pressure between the inlet and outlet is 40 kilopascals. A filter with a shock loss of this is installed in the pipe. The pipe coefficient of friction is 0.0013. Calculate. All right, let's calculate all this. So let's write down our given data. In fact, it's probably best that we show somewhat of a schematic illustration, right, of the problem statements, given that we are given the gradient, or given that the pipe is laid at a gradient of this, right? Now, seeing that we've been given the gradient here, right, it means the pipe is at an angle, right? It means the pipe is laid at an angle, right? And based on how the pipe is laid, the pressure difference between the inlet and the outlet is 450 kilopascals, right? 450 kilopascals. Now, what does it tell us? Right? If you remember from Mechanotechnics N4, right, we covered hydraulic systems on that subject. That is where we looked at what Bernoulli's principle is and the application thereof, where we look at, or where we looked at tapered pipes. So that would be horizontal tapered pipes. We also looked at inclined tapered pipes, and we also looked at vertical tapered pipes. We also looked at pipes with a constant diameter and what the implication of a constant diameter is as far as the velocity of the fluid flowing through the pipe. Yes, so we looked at Bernoulli's principle and the application thereof from that perspective, right? And from there, we learned that if you have a pipe and it is at an angle, right? So this pipe essentially would look like something like this. So that would be the pipe. So the gradient of this okay, make this, maybe let me make it a different color. So that's the ground. Well, maybe we can take that as the ground. That's the angle that the pipe is laid at relative to the ground, right? And then, of course, right, this would be the inlet, and that would be the outlet, right? Why am I assuming that this is the inlet and that is the outlet? Based on what given data do I make this assumption? Right? There's given information that suggests that the inlet is at the bottom and the outlet is at the top. What given data makes that suggestion? Are we still here?
Yes, sir.
All right. So my question is, what given data suggests that the inlet would be at the bottom and the outlet at the top? All right. So that would be the change in pressure. Right. Under normal circumstances, if you have an inclined pipe, right, or a vertical pipe, right, the pressure at the bottom, right, under normal circumstances, the pressure at the bottom will be bigger than the pressure at the top. Why? remember that pressure is equal to rho GH. Right? The specific weight remains the same. Specific weight is rho times G. Right? The rho depends on the fluid flowing through the pipe. So this will be the same. Right? G is constant, 9.81. So what determines, right? What is this thing? What determines the magnitude of the pressure, right, is the column of fluid, right? Is the column of fluid, or is the column of the fluid, right? Remember that this H is different from the H of potential energy. Remember, potential energy is mgh, right? The difference between these two H's is the reference point, right? The reference of this H for potential energy, right, is the bottom or is the ground, whereas the reference of this one is the top or the surface of the water. All right. That is why the pressure here will always be considerably more than the pressure at the top because of this H, the column of fluid. Right. So there is more column of fluid from here to the surface of the water than there is from this point to the surface of the water, essentially. Right. So given that the difference in pressure between the inlets and outlets is 450, that suggests that the pressure here must be bigger than the pressure at exit. Right. That is how we know that this here is the inlet and that is the outlet. Right. Based on this statement, that suggests that this is the inlet and that is the outlet. Right. Right. So we haven't been given P1, we haven't been given P2, but we have been given the difference between P1 and P2. Right. We've been given the pressure difference, which is that 450 kilopascals. Right.
Sir, can I ask you a quick question, sir?
Mhm.
If they ask you to work out the two pressures, say now the difference in height, since one is on the ground level, so there was no height. How do you work out the inlet?
Using Bernoulli's principle.
Okay.
You would then use Bernoulli's principle. If you had to calculate, say, one of the pressures, they would have to give you one of the pressure. Right? So they'd either give you,
Yes.
depending on which one they're looking for. So if they've given you P2, then you would have to calculate P1 and vice versa. Right? Either way, you would have to use this principle.
So when do you use that formula for the circle now? How
If you've been given the column of fluid, if you've been given the H.
Okay, okay, I understand.
Yes. Right. Now, here we've been given the change in pressure. So as far as what we've been given, we know we have the change in pressure, right? Which is P1 minus P2. That is 450 kilopascals, right? We've been given the diameter of the pipe. So being given the diameter of the pipe means the pipe is not tapered. It means it has a constant velocity. I mean, it has a constant diameter, right? Having a constant diameter, what does that tell us regarding V1 and V2? If the diameter is the same, right? If the diameter of the pipe is constant, it's not tapered. what does that tell us regarding the velocity? Right, the velocity will be more or less the same. So V1 is approximately equal to V2 because the diameter is the same. Right, the only time the velocity of the water will be different will be if the pipe you are looking at is a tapered pipe. That's the only thing that can change the velocity of the pipe. Right. So based on the fact that the pipe has a constant diameter, we can assume, in fact, it's not even an assumption, right? That suggests that the velocity is the same throughout, meaning that V1 is equal to V2, right? And then we have the gradient. The gradient is 1 in 100, right? The length of the pipe is 700. So from here to there essentially is 700, right? Now, how does that help us? Remember here you have H1, and then here it's here you have H2. Right, here you have H2, right, which is the height from here to there, right? You have H1 and then you have H2, right? Now, we haven't been given H1, nor have we been given H2, right? But we'll be able to calculate H2, right, looking at the schematic illustration of the problem statement, right? And the schematic illustration tells us that the pipe, seeing that the pipe is at a gradient, it means the pipe is at an angle, theta. Right, so we can work out H2, right, assuming that H1 is at the ground, hence equal to 0. Right. Now, we are looking for H2, and we have, based on our, what is this right angle triangle, right? The sides we have is this length of the pipe, which is our hypotenuse here. This is what we're looking for. So we can use sine theta. Right, so remember sine theta is equal to opposites over hypotenuse. Opposites, the side opposite the angle is H2. So this would be H2 divided by the hypotenuse, which is the length of the pipe. Right. Now, sine theta, right? If the angle that the pipe is laid at is small enough, right, sine theta is equal to tan theta, right? And based on the gradient being 1 in 100, right, it suggests that the angle is very small, right? Which means sine theta can be replaced with tan theta, and tan theta can be replaced or represents the gradient, right? So that is to say that we can replace sine theta with the given gradient, which is 1 in 100, right? So 1 in 100 is 1 over 100 is equal to H2 divided by the length of the pipe. The length of the pipe is given as 700 meters. So this would then be 700 meters. And then to solve for H2, or making H2 the subject of the formula, this would then be equal to 700 divided by 100. Are we clear here? That is how you would work out H2. Any questions here? No questions.
All clear, Mr. Mtet.
Right. So that is how you would then
So,
calculate. Yes.
I just want to ask you something. If they say calculate the head loss, does it mean the head loss H,
Sorry.
right? The question was asked, calculate the head loss, no? The total head loss. So is the head loss the H, the height?
The head loss. So, like I said, um, there's many ways in which we can express energy. Right. You get energy per unit mass. Right. Energy per unit volume and energy per unit. What's the other one? Okay, I forgot the other one. Right. But there's three ways in which we can express the energies. Right. In Bernoulli's equation or in Bernoulli's theorem. So when they ask you to calculate the total head loss, when they want you to calculate the total head loss, essentially what that is the energy per unit mass. Right? That is what it is. So when they want you to calculate the total head loss, they want you to calculate the total losses in the system from the perspective of the energy per unit mass. Right? Let me just show you this quickly. So, right, remember I said there's three ways in which you can express Bernoulli's equation, either by using the energy per unit volume. Doing that, that is how you express it, or energy per unit mass, right? That is how you express the energy per unit mass, and then energy. This is the one I forgot. The energy per unit weight, right? And this is how you express it, right? So the energy per unit weight, right? Remember that I said the standard energies that are expressed in Bernoulli's theorem. That's your pressure energy, your kinetic energy, and your what is this? Your potential energy, right? So the three variations of Bernoulli's theorem or of Bernoulli's equation, right, depend on what it is that you are looking for. So if you're looking for pressure, right, it is best that you express your Bernoulli's theorem or Bernoulli's equation in terms of energy per unit volume. That way, each of these terms would be in terms of pascals, right? Each of these terms will be in terms of pascals, right? And then if you're looking for velocity, right? Velocity is the determining factor for kinetic energy. Hence, if you're looking for velocity, it's best that you express your Bernoulli's equation in terms of energy per unit mass. That way, each of these terms will be in terms of meters per second. And then the one you're asking for, right? If you've been asked to calculate the head loss in the system, right? It is best that you express your what is this? Your Bernoulli's theorem or your Bernoulli's equation in terms of energy per unit weight. That way, each of these terms will be in terms of meters. So if you've been asked to calculate the total head loss, right? Essentially, what they're asking you to do is to calculate the total losses in the system from the perspective of the energy per unit weight. Does that answer your question?
Yes, sir, I'm all clear now.
Right. So I was supposed to have another session at 11. Let me just send a message to these guys quickly now, and then we can continue. Mm. All right. You did say that answers your question. Eh? Hello.
Yes, sir.
All right.
Right.
Right. So, like I said, we assume that this H1 is equal to 0, and this is how you work out your H2. Now let's look at questions. And then we are also given that F is 0,0013. Right. Now let's look at questions. 8.2.1. So for pipeline systems, it's always best that you draw the schematic illustration of the problem. Right. That way, it'll give you perspective as to how to approach the problem. Right. 8.2.1. Calculate the total head loss in the system if the flow is against gravity in meters. Right. We already knew that the flow is against gravity. Right. This suggested that. Right. So the fact that the pipe is inclined means that the flow is against gravity. Right. Also, the change in pressure, right, suggested that the flow is against gravity. So the flow flowing from here going in that direction means that it is against gravity. But that we have already, or we had already established just based on the given information. All right, so they want us to calculate total head loss. So to calculate your total head loss, you simply use Bernoulli's equations. All right. So for instance, if we use what is this thing? The energy per unit volume. So this is what you'll get. So P1, so the energy at inlet will be P1 plus half rho V1 squared plus rho GH H1. Now some of you maybe call this H1 Z, right? You can call it Z, you can call it H. It's up to you. And then outlet P2 plus half rho V2 squared plus rho G H2. Now they want us to calculate the total head loss in the system, which suggests that there are losses in the system. So the total losses in the system, right, you can refer to as simply HL, right? But now remember that we are using the energy per unit volume, right? So meaning that the energies that have to do with head, right, they have to be expressed in terms of pascals. And the way we do that is by using rho G H. So instead of HL, because we are using the energy per unit volume, hence each of the terms are in terms of pascals. All right, that is why here you would then have rho G HL. Right. So this is Bernoulli's equation that we are using. Right. We are looking for HL. So now we have to manipulate this, right, to make it sensible to calculate HL. Right. So making this term the subject of the formula, right? Making this term the subject of the formula, it means you have to transpose all of this to that side, right? Bearing in mind that we've already established that the velocity, right, in the pipe at inlet is equal to the velocity, right, in the pipe at outlets. So meaning essentially this will cancel with that because they're essentially equal, right? We also established that H1, right, H1 is equal to 0. So it means this term is also going to fall away, right? So now all we do is transpose this to that side, this to that side, making rho GL, rho GHL, the subject of the formula. So making rho GH sub L is equal to, then we will get P1 minus P2, right? We group those terms together, seeing that they're the same, or seeing that they are like terms, right? And then this becomes negative. So minus rho G H2, right? And then because we are looking for HL, it means we need to get rid of the specific weight. So we divide by rho G on both sides. So divide by rho G, divide this term by rho G, divide this term by rho G. So that cancels, that cancels. Hence, H sub L will then be equal to this minus H2, right? Now you can just substitute. So substituting P1 minus P2, remember we had already established that that is equal to the 450 kilopascals, right? We already established that. So we can replace P1 minus P2, right, with the 450. Remember, this is in kilopascals. So you convert it to pascals by multiplying by 1,000 divided by rho, right? Rho of water is 1,000. G is 9,81, right? Then minus H2. H2, we established that H2 is equal to the 700 divided by 100. So this is 700 divided by 100, right? And then when you punch this in your calculators, you are going to get your answer in meters. So what do you get? So what do you get here?
I get 38.872.
38, comma
872.
872 meters, right? So the total head loss will be this here, the 38,872. Right? So this represents all the losses in the system, right? Now let's look at 8.2.2. Calculate the velocity of flow through the pipe in meters per second, right? 8.2.2. Right? They want us to calculate the velocity of flow through the pipe in meters per second. Right? So with this one, we simply use the formula to calculate the total head loss. Right? The total head loss is equal to, now there are two losses here. You have the major loss, which is the frictional head loss, right, being given the coefficient of friction, right, suggests that you have a major head loss, which is the frictional head loss. And then we also have this minor loss, which is the shock loss here. Right? So the total head loss will be the sum of the major and the minor. And the major is the frictional head loss plus the minor head loss. Right? So this is equal to, seeing that you're looking for velocity, we are going to use 2 times F times the length of the pipe times V squared divided by G times the diameter of the pipe, right? Plus the minor head loss, which is given as this here, 6V squared over 2G. So 6V squared divided by 2G. Right? If you look here, we have this, 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 and this is what. So you substitute, all right? You substitute and then make V the subject of the formula, right? So A is 38,872 is equal to, so that's 2, F is 0,0013 times the length of the pipe was 700. So 700 times V squared divided by G, which is 9,81. The diameter of the pipe was 40 millimeters. So that's 0,04 meters.
Sorry, Mr. Mteto.
Uh-huh.
Is the length 700 meters or 700 millimeters?
Meters. There. 700 meters.
Meters, okay.
Yes. All right. And then, of course, here, 6 divided by 2 is 3. So we can have 3V squared over G, which is 9,81. Right. Now, here we have 38,872 is equal to, and then these are like terms, so we can add them. You have 2 times 0.0013 times 700 divided by 9,81 times 0.04 plus the 3 over 9,81. So here I am getting 4,9439 V squared. All right. And then because you're looking for V, all right, we have to make V the subject. In making V the subject, right, you have V squared. You have to get rid of this, making sure that the coefficient of V is 1. So you will have 38,872 divided by the 4,9439. Right? And then also we have to get rid of the squared. So we use the square roots on either side. Hence here we'll be left with V. And then this side we'll have the square root of this. Right? And then this should give us a V. So the square root of 38,872 divided by 4,9439. So I am getting here 2,804 meters per second. Are we getting the same thing?
Yes, sir. Yes, Mr. Yes, sir.
Okay. Well, that is how you would calculate the velocity. Let me see here. I'm just thinking if there is possibly another way we can calculate the velocity. I don't think there is. Yeah, I don't think there is. Right. So we can stick with this. With this. With this method. Right. For this problem statement. 8.2.3. Are there any questions for 8.2.2? No questions. Right. So let's move on to 8.2.3. Calculate the head loss due to friction in the system in meters. Right. Like I explained. So here it's pretty straightforward because they said calculate the head loss due to friction. That's obviously HF. But they could have said calculate the major head loss in the system in meters. Right. Like I explained, the major head loss is the frictional head loss. That's HF. Right. So here they made things simple for us, or for you rather, and said calculate the loss due to friction, and the loss due to friction is HF. Right. So all they want is for you to calculate this here, the frictional head loss. So that is 8.2.3.2.3. They want us to calculate HF. Right, HF, we've already established, is equal to this. So now you substitute 2 times 0,0013, length, which is 700, and then V we've calculated and got 2,804 squared divided by G, which is 9,81. The diameter is 0,04. Right, so this is 2 times 0.0013 times 700 times 2,804 squared divided by 9,81 times 0,04. So I'm getting here 36,467 meters. Are we getting the same?
Correct. That's correct. Getting the same.
Right. Now, based on this magnitude, if you look at the total head loss is 38,842. So 38,872 minus the answer is 2,405, right? Which means indeed that the frictional head loss is the major head loss in the system. Does it make sense now?
Yes, makes sense.
All right. All right.
So I just want to ask you something. The friction one you worked out now. Is that formula always the same?
Sorry?
The formula for the friction,
What
is
about
that
it?
always the same?
So there's two variations for calculating the frictional head loss. Remember that how we calculate the frictional head loss is based on Darcy and Chase's formula, right? And as far as Darcy's formula, you get two variations. This is one of the variations where we use velocity. The other variation is one for the discharge or flow rate. So that one will be, what is this? It's F times L times Q squared divided by 3,026 times D to the 5. Right. So for HF, you either use this variation or this variation. Right. You are going to get the same thing. Right. So the two variations are to make things convenient based on either what you need to calculate or what you've been given. Meaning, if you have to calculate HF and you've been given V, then you can use this variation. Or if you have HF and you have to calculate velocity, then you can use this variation. But if you have to calculate HF and you've been given the flow rate instead, then you can use this variation and it will give you the same thing. Similarly, if you've been given HF and you have to calculate the discharge, instead of you having to calculate the velocity using this and then calculating the discharge using this formula, you can simply use this formula or this variation of Darcy's formula to calculate Q. Are we clear? Hello?
I think the answer is clear.
Sorry? Are we sorted?
Yes, sir, we are sorted.
Right. Now also with this one, in the formula sheet, maybe, because I'm not sure, but sometimes this is how it is expressed. HF, they say 4 times F times L times V squared divided by 2 times G times D. Right, so all I did was I said 4 divided by 2, which gives us the 2. Right, that is why I got rid of this. And then here, instead, I have 2. It's the same thing, though. Do you understand what I mean here?
Yes, it's clear.
Right. Are there any more questions?
From my side, no questions. Just a request. Maybe after your next class, will it be possible that you share the video? I mean, the recording. The recording.
Yeah.
And also the other questions that you said you share that are similar, so that we can work on them.
Yeah. Will do.
Thank you.
All right. All right. If there are no more questions, I guess we are done with this session. All right. I will be available in the group if you have any questions. So say you try some exercises and you just want to confirm something, right? You can send them in the group. I will respond in the group. Nah.
All right. Thank you. Thank you, Mr. Mtete.
All right. Cheers, guys. All the best. Nah?